Hello. Hello, I'm Tianyu Wang. I'm a PhD candidate at Duke CS. Today I'm going to talk about our work on Lipschitz bandits. Our paper, at a high level, is about a practical Lipschitz bandit algorithm that learns the partition. Our analysis links decision trees to Gaussian processes in a bandit setting. Let's first recap what is a bandit algorithm. In one line, a bandit learning algorithm is a sequential decision-making process that balances exploration of the decision space and exploitation of the good options. For example, let's say the reward function is this blue curve. The blue curve is not directly observable, but we can select some points to obtain function values at the selected points. The question is how to sequentially select points so that we're overall not too far from the optimal function value. We select some points or place some arms to learn this function and make decisions at the same time. At the end of the day, we want good arms to be played more often. The bandit problem has a long history. It can go back to Thompson in 1933, and many excellent authors have contributed to this field, but we won't be able to cover all of them today. For our interest, Lipschitz bandits are most relevant. Lipschitz bandit was called continuum arm bandit in early stages and was studied by Kleinberg. Later, zooming and HO were invented. Different versions of this problem have also been studied. The general recipe of existing work is discretize the arm space and treat it as a finite arm problem. Previous methods suffer some problems. First, the discretization is too restrictive, and second, after the discretization, each region or bin or box in the discretization only cares about itself. Our methods aim to solve these problems. As we mentioned before, previous methods are usually too restrictive in discretizing the space, and we will learn this discretization instead. Suppose we are in this situation, the blue curve is a true but unobservable reward, and red crosses are the arms played and rewards of the arms. When it comes to discretizing this region, previous methods will treat the entire region equally and will typically split at the midpoint. Our method will look at the reward landscape and discover that we should probably discretize here, since there is a jump in the reward. In this kind of situations, our method can better capture the reward landscape. Our method follows this routine. Each time we learn the discretization and estimate reward with respect to the discretization, and then we compute an upper confidence bound, or UCB, which is the estimate plus the uncertainty of the estimate. Here the uncertainty is a Hofding's term plus a Lipschitz term. We then play an arm to maximize the UCB. Here is an example run, with arms indicated by red dots at the bottom. With some initial observations, we learn the discretization, we make estimates, we compute UCB, and we play an arm to maximize this UCB. We repeat this process, and in the end, arms in the good regions will be played more often. We also have some other intriguing observations listed here. Thank you.